Oh, there are some? Okay. So maybe I need to remove mine? No, I need to remove mine?
No, I think yours is the first one. So
okay. Okay.
Yeah, I'll find out who has the computer.
Oh, except to say she has. Yeah.
Yeah, we're all set up. We're loaded, ready to go.
All right, let's get started. It's 12:03, so we're ahead of the Harvard. So welcome back, everyone, for the afternoon in-conference session. So we'll first start with the research topic that we'll meet. All right, so we'll talk about, I guess, astrochemistry is pretty on.
Yeah, somewhere, but I'm afraid that it will. Does it work like that? Okay. So yeah, good afternoon, everyone. And so first, I would like to thank the organizer to give me the opportunity to present this work. So I recently joined the group of Karin Oberg here at the CFA. And the work I'm going to present today, I started it when I was a postdoc in the group of Eric Herbst at the University of Virginia. And we did this work in collaboration with the team of Valentine Vaclam from Bordeaux in France, and some of her students from which have now moved also to the US. And so this is about a new study of the chemical structure of the Orsted Nebula, with a special highlight on the influence of grain surface chemistry. And this study was recently published in ANA, so I invite you to look and see the paper if you want more detail, but I'm going to give an overview today. So I will first present the context of this work, which was the detection of a wide variety of molecules in the Orsted Nebula, so mostly thanks to a recent line spectral survey. And so from this observational data that has been published, we developed a model, so a gas screen chemistry model, so it's a time-dependent model, in order to understand the distribution of this molecule in the Orsted Nebula, and also the abundances that were derived from the observations. And so I'm going to present how our results can be compared to the observations. So the Orsted Nebula is a photodissociation region, so situated in the Orion B molecular cloud. So it is approximately 400 parsec from us. And the particularity of this photodissociation region is that it is seen nearly edge-on. And it is illuminated by the Sigma Orionis star, which is situated at approximately 3.5 parsec from the edge of the Orsted Nebula. and it impinges the Olsen Nebula with a UV flux of 60 times the interstellar radiation field. So it makes that this nearby photodissociation region is an ideal opportunity to study the physical and chemical structure of PDR, so a photodissociation region. And so mainly two positions were observed during the 15 past years, and they are only a distance of 35 arcseconds from one another, which correspond to less than 0.1 parsec, but they have been shown to trace a very different environments. So this was first pinpointed by the detection of DCO plus in only one of these two positions, so the most embedded one. And from this observation, Petit et al. 2007 shown that the temperature, derives a temperature of 20 K for this position, which seems to characterize more shielded dense core position, whereas the other position, so the less embedded one, was have been shown to trace a more illuminated region. So from this observation, so the HCO observation, Gérin et al. 2009 derived a temperature of approximately 60 K. So highlighting that this position was probably more impacted by the UV flux from the star. And so this meant that the Olsen Nebula is probably a good opportunity to study the transition from a warm gas, where photodissociation processes and photoelectric heating can occur, to a more denser and shielded gas, where high deuteration fractionation is taking place. And so this is why the Olsen Nebula is probably a good template to use as a reference for PDR model in order to benchmark our model, and after to be able to analyze more complex galactic observational data, or even extragalactic data. And so here I'm going to briefly present what the survey provides. So it was the spectral line survey WHISPER, for which Jérôme Petit was the PI. So they observed these two positions I just showed you with the IRAM 30-meter telescope. And so the aim of this survey was to have a detailed comparison of the two positions, so the UV shaded one and the UV illuminated one. So they observed approximately 30 species, plus their isotope log from small to complex molecule up to 7 atoms. And so from this observation, in our study, we focused on the 17 molecules. So I classified those molecules here by molecular family. So there were some organic molecules and their precursor, some nitriles, some small hydrocarbon, and only one fluorine-bearing species. And now here I'm going to come to the modeling part of the study, so how we build the model and how we can compare the results with the observations. And so in order to well understand the distribution and the abundances of this observation, so we build a model that starts from a 0D model, so for which we are going to first form a starless dense cloud where the sigma Orionis star will be formed and the photodissociation will form also. So for that, we run a classical dense cloud model, so for which we use as a physical condition a typical temperature of 10 K, a density of 2 × 10⁴, a strong visual extension, so we took 30 magnitude here, and for the cosmic ionization rate, we took 5 × 10⁻17, and this value, we use this value specifically because it was constrained by previous observations, so from Goitia et al. 2006. And from this study, we also took the initial chemical composition, except for the fluorine-bearing elemental abundances. We took a value which seems more appropriate to the model, and also which seems to better reproduce the observation of CF+, as I will show you in a minute. And so this model So it's a rate equation model, so that takes as an input a chemical network. So for that, we took a very recent chemical network. And so it will compute the abundances of each species at each time at each step of time until a fixed time that we determine. So we run the simulation for 1 million years. And beside that, we also build the physical structure of the Orsted Nebula. So that is to say the temperature and density profile of the Orsted. So for that, we use the Meudon PDR code. And we use for that also observational constraints. And so once we have built this first starless dense cloud model and this physical structure, we consider that the star is born. And we run a subsequent 1D model, so which will take into account the physical structure and which will compute the chemistry for each position of this physical structure. And so for that, we started this 1D model from the output chemical abundances of the first 0D model, and we run this model for 1 million years once again, and so with the same chemical network than the previous one. So here are the results that we obtained. So those figures represent the abundances after 1 million years from the starless dense cloud stage. So the abundances are represented here as a function of the decreasing visual extension. And so the observations are also represented with the vertical error bars representing the observation. The horizontal error bars represent the visual extension ranges where our model best fit the observation. And finally, the grayish boxes represent the indirectly constrained visual extension from the observation. And so what we mostly found from the model is that we could reproduce most of the observation, but considering that the observations are probably not all co-spatial, and especially we couldn't reproduce some of the observation. So for the small hydrocarbons, for instance, so for the very edge of the Orsted Nebula, so this is the third position that were observed after the spectral line survey WHISPER, which was called by the observer the pH position, where they observed high abundances for some of the hydrocarbons, and our model was not able to reproduce these abundances. So even for earlier time, where our model can produce more of this molecule, we were still underestimating the observation by more than order of magnitude. And this might highlight that we still need to constrain the chemistry of the small hydrocarbon, especially in very high UV illuminated region, where maybe other processes could occur. So in our model, we are considering what we called bottom-up chemistry. But for instance, in those regions where pH are supposed to be also, it could be also a top-down chemistry where some pHs could produce some of the amount of these hydrocarbons. And so here, now I'm going to focus on the CF plus observation and show you how it can help to constrain the model. So for that, I ran 3 different models. So the first model is a model with higher fluorine elemental abundances. I told you I choose to took. And we see that with a lower elemental abundances, so the RAN model here, we are not able to reproduce the abundances. I mean, we reproduce the abundances not as well as with the blue model. So this was the value that was previously used in previous model. And the third model one is a model where we updated the chemistry for the fluorine chemistry. And we see that just by implementing this reaction in our model, it can improve how we reproduce the observation. So it's also very important to be able to constrain this chemistry. So we need 1 minute. Yeah, we need the feedback from the experimentalist and the theoretician on the chemistry. This is very important to feed our model. And so here I come to the summary and the future work that we still have to do. So to summarize here, so for the model, we first ran a 0D model, and that we coupled with a 1D model once we build the first star dense cloud and the physical structure. So the 1D model will take into account the UV flux from the star. And what we'll highlight in particular in this study is that we need the grain chemistry in order to reproduce the complex molecule abundances observed in the Orsed Nebula. We also need the time-dependent chemistry because we show that we need longer time scale for the chemistry for the core position. And we also highlight in this study that the most efficient way to release the COMS in the gas phase was the chemical desorption and not the photodesorption. And this is probably because the PDR, the Orsed Nebula, is a smooth PDR because the UV flux is not very high. So this is probably why photodesorption is not very efficient for this specific region. But future work will be to further investigate the desorption probability, the chemical desorption probability, sorry, because in my model, it is not, it can depend on each molecule and it is not yet taken into account in the model. Also, we would like to be able to compare our predictive results with extended observation and also with coming GWST data, because in the paper we are also providing some ice abundances. And also we could also investigate more some part of the chemistry. So for instance, the orthotoper ratio of H2CO have also been detected in the Orsed Nebula, and which is very interesting is that different orthotoper ratio are observed depending on the position. So from this nuclear spin chemistry, we could also provide other diagnostic on the gas. So it could be also very interesting. And once the model will be well benchmarked, we could also explore other PDR with this model. So I stop here and thank you for your attention.
Get some light here.
Fix the lights. And just the tech support.
All right, so time for questions. Good question while we set up for next talks. Would the clumpy structure affecting the model?
So you mean the clumpy structure in the third dimension one?
Yes.
Yes, probably because for the moment we don't have any constraint, observational constraint on this line of sight. So yes, it could. So it's 60 times the interstellar radiation field. So it's not very, it's not a very bright. So it's very smooth PDR. So the UV flux is very low.
All right.
For a PDR.
All right. Thank you. Thank Romain again. Maybe we should summarize instead of trying to complete that.
I'm sorry. You can skip that.
Can people in
Hi,
the
it's
back,
not you.
okay?
Yeah, no, I'm just setting it up. Okay.
Thank you. This is on, right?
Yeah, you can put this in your pockets. Here.
Okay, well, just have 2 minutes, so be quick.
All right, so now we have a set of introductory talks. Each of those are 2 minutes.
Thanks.
So the first one is Luan. He's going to tell us about hierarchical fragmentation in process molecular cloud.
Yeah, hi everyone. So my name is Rivas Pokhrel. I've been working here since past about 2 years with Professor Phil Myers. And I have been working on this project, hierarchical fragmentation in the process molecular clouds. In the left, that's kind of very hand-wavy cartoon picture of all the different structures in a molecular cloud. I know Alisa doesn't like boundaries, and I have a lot of boundaries in there, but that's just a cartoon picture, and I have a reason to make that. So I'm just showing all different scales arranged according to their size, and also the densities, lower densities to higher densities at the center, starting from clouds that are more than 10 parsecs all the way to the central disk and the star system. And I have looked at this scenario in persist molecular cloud. I started with one specific size scale of envelopes, actually with the SMA data, but then we expanded our regime to other scales also. So this is one example of the hierarchical structure seen in the persist molecular cloud. We have the whole cloud itself with different clumps. If we take one particular clump, this is L1448, then we see the presence of different cores. Take one core, this one, and then we see presence of different envelope scale structures. Again, take one envelope scale structures, different protostellar objects. Now, these all are probed with different instruments. For example, these two with Herschel, core Scuba, this envelopes SMA. This is where I devoted more than like 80-90% of my work. And then protostellar objects with the VLA, John Tobin's Van Damme work. So I have done this study for all these substructures inside the Perseus molecular cloud. And the idea of this study is to compare the number of the children objects for each level of hierarchy. I would compare the number of the children objects with the genes number of the parent object, where genes number is calculated assuming either it's entirely thermal support or a thermal plus non-thermal support. So for non-thermal, I have used various gas tracers again, for example, ammonia tracer, the typical line width obtained from previous observations with ammonia for core, N2S plus for envelopes, and so on. So I am very happy to talk about, there's a lot of things that go on in this study. So I'll be happy to talk later about this. And if you are interested with this plot, then I'll just tell you the conclusion for now, but we can chat later. We find that the hierarchical structure formation is consistent with inefficient genes fragmentation, and where efficiency is defined as the ratio between how many numbers are formed and how many are predicted by a certain support mechanism. And we find that the thermal genes efficiency increases from the large scale, like 0.06, to smaller scale. It goes on increasing as we go into smaller and smaller objects. Thank you.
All right. Thank you, Raj. So next one, we have Elaine Winston.
Lost scatter points. It's a very sorry. It's going to take a little while to load because I put a large image in there, and it's hopefully it's turning out a little bit. This is so basically I'm working now with Joe Hora and Vocal Dolls over in 160, so we're getting a little lost over there. We are working on a survey of the glimpse data from IRAC, and mostly so Spitzer IRAC data. And we are focusing on the outer galaxy. So as you know, all of the Spitzer data, all the papers that have come out to date are mostly focusing on the inner galaxy, on regions of star formation that are already kind of well known and well studied. However, this is the inner galaxy, it's a denser region, it's a higher metallicity. We don't really know what's going on in the outer parts of the galaxy. So our goal is to take all this very abundant data. It's probably not showing up very well here. I think it's fine. We can. Oh, you should say. Okay, it's a really pretty image. They've done a lot of work for this data. So there's a lot of stuff that's going on out here in the outer parts of the galaxy. Obviously, it's showing the inner as well. But the smoke field that we're working on at the moment is looking at through two of the outer spiral arms here in the Sagittarius. So this is a close-up of the field. It's about a 21 square degree field. It has about 3 million sources in the field. And at the moment, we are doing kind of a standard analysis. We are looking at the spatial distribution, identifying YSOs, getting surface densities, finding clusters, and basically trying to find the best way to do this, and so that we can apply it to the entire data set. So this is basically the contents of my poster. If anyone has any ideas on the best way to do this, on using machine learning to make this process faster or better, please come and talk to me. So I think that's perfect.
Thank you.
Thank you. Yep. Got him.
Sure. Yeah. All right. So next one we have Fang Xiong. He's going to tell us something about.
Fermentary structures.
All right.
Hi everyone, I'm Fang Xiong. I'm a pre-doc at SAO. I'm working with Chizo. So I just started my pre-doc here. So just talk about my previous work. It's 2 plots on the upper panels and my previous work. So I used to work with a single dish data, and we use 13CO to identify about 12 fermentary structures at the G115 regions. And 4 of them are also detected at the C18O. And we further investigate these varialized CO clumps and YSOs. It turns out these varialized CO clumps and YSO are mainly located at least 4 fermentary detected with C18O. So we think, we conclude that at least 4 fermentary detected with C18O may contain potential star formation activities. And right now, I'm basically working with this VLA data. So we have a VLA observation towards NGC 6334. It's mapping the whole region in ammonia to investigate the mass accretion along the fermentary structures. And we got about 58 pointings covering the whole the nut-scale fermentary and these massive clumps. IN to V. So what I got is a pipeline calibrated data, and it turns out this pipeline calibrated data is poorly calibrated. So right now what I'm doing is start from the beginning and calibrate these 58 pointings by myself. Yeah, okay, thanks. Yeah.
Next, we have Shay Stoll, who will be speaking on DR21.
Yep. All right, hey everybody, my name is Shay Storm. I'm an SMA fellow postdoc here at the CFA, and I wanted to present some work I've been doing with Chizo here on the SMA view of DR21. So here on this side, we have a beautiful Herschel 3-color image of the DR21 region in Cygnus X in our Milky Way. And then to the right of that is an ERM. This is a 11 arcsecond 1 millimeter continuum map, and there's on the order of over 3,000 solar masses both in the south and in the north of this region. But it's in the south where you have DR21OH, you have more of the massive star formation, more of the infrared luminosity. So it's kind of an open question of why is this a much more active part of the ridge compared to the north. So before I got here, we did a contiguous mosaic of this full 2 parsec long region of the DR21 ridge. Plenty of these cores have been observed before in detail, but never before getting this full 2 parsec long structure. So cutting to the gist of what I want to show here is we quantified the structures in the SMA mosaic, and what we're plotting here are mass versus size for the north versus the south. We have ERM, PDBI, and SMA structures here, and I plot the empirical massive star limit that Jens Kaufman and Tushara and that others here in 2010 published, and they made the point that not all IRDCs will form massive stars. They found that you really need to be above this massive star limit, and you see that the structures in the southern part of DR21 do appear denser. So why do we have so much more infrared luminosity from the south? Well, perhaps it's because that's where the structures were pushed to a higher density. Why were they pushed to a higher density? Well, there's evidence that there's more intertwined filaments in the south. Chizo's collaborators have really nice Karma H13CO plus data showing 3 filaments at different kinematic velocities. And Herschel team has used continuum to argue in the DR21 ridge that there's more intersection of filaments in the south compared to the north. So come chat with me if you want to discuss more of this DR21 picture. Thanks.
Next, we have local polls.
Okay, hello everybody. I'm Volker Tolz, and I just give you a quick overview of the primary projects I'm working on, which take about the first 200% of my time. And the first one is a Herschel analysis of the clump 2 region And in the galactic bar, it's located at about a longitude of 3 degrees. And a very complex region. If you look at the CO 1 to 0, you find emission from 0 velocity to about 200 kilometers. So it's really hard to entangle. The second project I'm working on is the data reduction for Gusto. Gusto has been approved earlier this year as a SMEX ultra-long duration balloon, and it will fly for about 100 days around the South Pole. And during that time, it's planned that it will map the galactic plane from minus 25 degrees to about 25 degrees and a latitude of plus minus 1 degrees. And it will carry 3 receivers with 2x4 pixels each to observe C2, N2, and O1. The expected launch is about December 2021 during the Arctic summer. And the third project I'm working on is a all-sky survey called SphereX. The PI of this project is Jamie Bock at Caltech, and our participation here, I'm one of a member of people here from SAO, which are under the lead of Gary Melnick and Matt Ashby and Karen Erberg, are on the team. And our science theme is the origin of water in planetary systems. And what we're doing, we're taking spectra from 0.75 micrometers to about 5 micrometers and want to measure the ice absorption in these spectra. And we expect that our science goal is a minimum of 20,000 spectra. The expectation right now is more that we probably get 1 million spectra or more. And the launch is for 2022, and right now we are in a phase A study. That means we have competitors, and we have to get rid of these competitors that we can move on to phase B, and it's quite funny. It seems like the competitors eliminate themselves. Whoever is interested in these can talk to me afterwards. Thank you.
Thank you. We are moving on to our next research talk by Ida Ahmadi. She'll talk about coals. This is the Iron Lodge program to study HIMAS star formation.
Would you like the lights on or off?
Off is fine.
Off is
Yeah.
fine? Okay, this works.
Whatever you want. Okay, hi everyone. My name is Ida Ahmadi. I'm a PhD student at the Max Planck Institute for Astronomy in the group of Henrik Beuter. And I'm excited to tell you today about our ERAM large program called CORE, and it's not an acronym for once. So the large program aims at basically studying high mass cores, high mass fragmentation processes in order to understand the early phase of star formation in the high mass regime. So my thesis will be focused more on the disky side of things, so I will give you a bit of a motivation on that end. Until about a decade ago or so, we didn't know how high mass stars get their mass. It was expected that the radiation pressure would be too much for these high mass cores to be accreting enough material. But works by Mark Krumholtz and Rolf Kuiper showed that, in fact, we could add mass to these cores and create such high mass stars through disk accretion. Unfortunately, observationally, we're lagging a bit behind. Due to the clustered mode of high mass star formation, as well as typically large, far distances, we have been actually a bit behind because we need high resolution studies to be able to really resolve these fragments. So actually, Keplerian-like structures have been observed so far around B-type stars, but those around O-type stars have only been done more recently. So there have been a couple of papers in the past couple of years by Catherine Johnston and John Illay. And this year, Riccardo Cesaroni presented a sample of 6 O-type protostars, for which he found disks around about half of them. So to that end, we decided to make our own large program at ERAM in the northern sky. And so what we did was we proposed for a sample of 20 objects, highly luminous, so more than 10 to the 4 solar luminosities, at distances less than 6 kiloparsecs. And the data was observed from 2014 to January of this year in dust continuum and line observations at about 1.3 millimeters. And we did multi-scale observations, so we observed with the NOEMA interferometer, which is an updated Plateau du Bure interferometer. So they're basically adding about 6 antennas to Plateau du Bure, and it's called NOEMA. And we observed in 3 different configurations, in the A, B, and D. The D configuration is the most compact, and the A is the most extended. And our combined data set resolves the cores at about 0.3 arcsecond resolution. So at a distance of about 2 kiloparsecs, this is about 600 AU scales. We also obtained 30-meter telescope data in order to be able to cover the missing flux. And basically, in combination of our 30-meter telescope and NOEMA data, we're able to probe many different scales. So let me show you our spectral setup. We cover the range of 217 to 221 gigahertz continuously at a spectral resolution of 2.7 kilometers per second. So here's an example spectra for AFGL 2591 for this regime. And then we have 8 zoom regions at higher spectral resolution of 0.5 kilometers per second, which we have put on really interesting molecules like disk tracing molecules and so on. So first I will show you our dust continuum results. So here you see a 50,000 by 50,000 AU box, and here's the dust continuum at 1.3 millimeters for IRAS 23385. So you can see that we resolved a couple of cores here, and the full sample looks something like this. At first glance, what's interesting is that here we've put all the sources at the same linear scale, so you can compare each box with the other. And what's interesting is that we have cases for which we just resolve really singular cores, and then other cases where we see, up to more than a dozen cores. And so this is a work that has been done by Henrik and is to be submitted soon. And what we find is that the fragmentation is actually set more so by the initial density structure and not so much by the turbulence. So if you want to talk about this, you can talk to me afterwards. I'm going to focus more on the disky side of things. So let me just zoom in on each of these panels and show you the dust continuum contours. So I've now zoomed in. So here, for example, you see the 2 cores, 1 core, and so on. And what I will show you is the moment 1 map, so the intensity-weighted peak velocity of a disk tracing molecule. And we basically recover rotating structures around most of our objects. We have a few exceptions, which are shown by the stars. So for these, I'm actually showing the moment maps for formaldehyde, which is a more diffuse tracer. And in these cases, we're not able to detect any emission on the position of the cores, really. And for these special cases, we have to study whether these objects are perhaps at a different evolutionary stage than the one we were looking for. So let me now focus my study on just one source and show you what we can do with this data set. The source I will be focusing on is this one down here. It's called W3H2O. It resides in the W3 cloud. Here's the schematic of the cloud in MSX 8 micron image. So you have in the north, W3 north, W3 main, and the core that we're interested in is in the center. So I will zoom in on this and show you again in color the MSX image, and then in contours the Scuba 850 micron, so you can see that most of the mass is concentrated to the right. And then what NOEMA actually sees in this core is the innermost couple of pixels. So here's our view with NOEMA. And we really recover a couple of clumps inside. So to the right is W3OH, and to the left is W3H2O. The naming is due to the existence of water and OH masers at these positions. W3OH is an ultra-compact H2 region, which is powered by an OB-type star. So at 1.3 millimeter dust continuum, we basically mostly get the contribution from free emission. And since this object is more at the later evolutionary stage, I will focus most of my work on W3H2O, the source to the left, which has a luminosity of about a few times 10 to the 4 solar luminosities. So W3H2O is one of the most interesting sources in our sample. It's extremely chemically rich, so we have a lot of data to study chemistry on this source. So here's an example of our full wideband data. And the molecule that I will focus on, the transition that I will focus on is the methylcyanide 12 to 11 rotational transition, which then splits into 6 different K components. So here from K code 0 to about K code 6. And what I will show you is, again, the moment map for methylcyanide K code 3, because it's the least blended line. And that looks something like this, where we see a clear velocity gradient in the east-west direction. Here in the contours, you see again the dust continuum. And what's misleading is that the clear velocity gradient at first sight might make you think that this is a disk, but clearly you can see that the clump has actually fragmented into a multiple object. So we can also look at the moment zero, so integrated intensity map in lines. And in fact, what we find is that the clump has fragmented into a couple of sources. So even a more diffuse tracer like formaldehyde shows that, that it's indeed 2 sources. So here we have an example of core fragmentation where you have a clump which then fragments into a left and right is what I will refer to. Cores with either at least 1 or even more objects in the center. So we can then study the kinematics of each of these clumps. So here in the contours, you see the dust continuum, but I've only imaged the most extended configuration here. So you get slightly higher resolution, and you can see the velocity gradient for, so the color is the moment 1 map again in methylcyanide. And so there's a clear velocity gradient in this direction. And what I can do is make a position velocity diagram. So here I make a cut along this line, which corresponds to this axis down here. And then in the y-axis, you get the velocity. And here you can clearly see these high velocity features close into the center. And on this side, it's a bit harder to deduce anything because actually this cut is going into the emission from the core to the left. So what we can do here is to just overlay a theoretical Keplerian-like curve on here. So this is corresponding to a 10 solar mass object. So we can again do the same game for the left core. And for the left core, we see this velocity gradient in this direction. But the position velocity diagram is more of a rigid body type rotation. So for this case, we can tell that there's differential rotation about the center, but for this one, it's a bit harder to deduce such a conclusion, even though we get a slightly higher velocity bob. So then what we can do, so I should also mention that both of these cores actually have bipolar molecular emission. And so what we can do with this is then to actually get a temperature map. So what we do is we use the methylcyanide ladder in order to fit it under local thermodynamic equilibrium. And here, for example, you see the fit to the K equals 4 to 6 line, which corresponds to a temperature of about 160 Kelvin. And we do this pixel by pixel and get a temperature map for the entire object, which doesn't actually have any specific distribution, but is warm at about 180 Kelvin. So what we can do with a temperature map is to study the stability of this source. So we do a two-rate stability analysis. So the idea is that for a differentially rotating disk, the shear force would be providing an added stability against collapse. So this was quantified by Toomre in 1964, where on top you have the temperature and the sound speed and the epicyclic frequency. In the case of Keplerian rotation, this is the angular velocity. And then in the bottom, you have basically the gravity. So you have sort of an interplay of shear and temperature providing stability against collapse. And so for Q values below 1, you're in the unstable regime. And so what I do is I create a Toomre Q map. So in this case, I have assumed two 10 solar mass objects at the positions of my continuum peaks, and assumed Keplerian rotation about these two objects, and I've created a two-metric Q map and then stitched them together. So you can see here that we have unstable regions, so if you make a cut in the middle, each of the cores is sort of asymmetrically unstable. What's interesting is that actually the position of this instability here coincides with a continuum peak in our most extended configuration, which could hint a further disk fragmentation at this position, but we don't have the resolution to completely conclude this fact. This result is complementary to theoretical models of Ralph Pudgett's students, so Michael Klassen, who did this work in 2016, where they basically do radiation hydrodynamic simulation, and they evolve a 200 solar mass clump. And so here you can see the two-metric Q map after 14, 18, and 21 kiloyears, with the central objects ending at 20 solar mass, 28, and 42 solar masses. And so they also see this asymmetrically stability, which then in their case goes on to create sort of spiral arms and with an increased period of accretion at this stage. So let me just conclude. I hope that I've shown you that high-resolution studies are needed in order to understand this early phase of high-mass star formation. We detect rotating structures around most of our objects and find different modes of fragmentation, where we see isolated cores versus highly fragmented cores. And then in the case of W3H2O, we have a core that fragments on larger scales, and on smaller scales, it fragments through disk fragmentation. An outlook for my project is to apply a similar analysis in the future to the rest of the sample. So with that, I would like to thank you and take your questions.
So we have time for questions.
Yes. So actually this plot here, there's a paper by Chen, 2006, that actually basically models this rotating structure, and they find this to be basically a binary rotation. So the rotation that you see here is due to binary rotation. Yeah.
So you show the fragmentation when you have sources put in the same linear scale, and some of the objects is, I believe, was a Cephas PV-Ceph or Cephas A that show less fragmentation. Now, do you consider, I assume that you also have primary beam, that sources outside of primary beam that you'll not be able to detect?
So we've done primary beam correction for the...
But the objects outside of primary beam will not have sensitivity to detect them. I'm just wondering whether those are biased because of primary beam, that you see fragments
closer to the center.
At the center of the map.
Perhaps, but I think we set our phase centers obviously at the highest peak, right, at the highest mass luminosity.
Other questions? All right, let's thank Ida again. So now we have 5 introductory talks. We'll start with Sarah.
While we're getting that set up, I'll just say that at the very end today, we're going to put up another couple of pages for the unconferences for tomorrow. So if you have any ideas you don't want to forget, you can write them down today. Otherwise, please come early tomorrow and write them down so I don't have to pressure everything again in person.
All right. Hi, everyone. I'm Sarah Sadavoy. I was a postdoc over at Heidelberg, but now I'm here at Harvard, so this is excellent. So what I have here is actually my poster, because I was lazy and didn't want to make a new slide. And so just very, very briefly, this is submitted work to correct Herschel observations of small maps of low mass clouds. So you need to use different techniques in order to do this, and that is what this study in particular tried to do. If you're interested in learning more, please feel free to come see me or go read the poster. But what I'd rather highlight is some recent ALMA observations. For anyone who was in the magnetic field unconference session earlier today, you already heard all about this, but I just want to do some self-promotion. This is polarization observations at 1.3 millimeters with ALMA, Cycle 3 project, looking at 32 young stars in Ophiuchus. This is the first large survey of polarization with ALMA that I'm aware of. The data were just delivered like a month ago, even though this was a Cycle 3 project, so I'm still working through imaging everything, but we've got some really pretty images. So these are both young protostars. This is a Class 0 source, the canonical Class 0 source. This is a Class 1 source. And yeah, we're seeing some very interesting features, including observations that suggest that polarization is through dust scattering rather than magnetic fields, which I hope to explore further. Again, if you have any questions, feel free to come and speak to me. Thank you.
So next we have Daniel Callanan.
Hi everyone, I'm Daniel Callanan. I'm working with Chiju here. I'm doing my pre-doc. Basically just started, so this project is in its infancy. But I'm taking a chemical approach to the CM Zoom survey, which I'm sure many of you have heard of. You'll hear a bunch more about it this week, I'm sure. I'm probing various clouds throughout the CMZ. I'm studying how the chemistry within these clouds vary as a function of environment. Things like silicon oxide, which trace shocks, are found throughout. Dense core gas tracers are also found without. This gas is all above a density of 10 to the 24, so this is a very exciting region. But I thought I'd treat you to some M83 data, which is a project I've been working on for the past year. This is a nearby bispiral galaxy. I've been studying the center of this region with some ALMA data. This is 0.5 arc-second resolution, which is about 12 parsecs at this distance. So this is the HCN integrated intensity map. We also have HCO plus data. Plotted on top of this are 45 clusters found by Harris in 2001 in this region, which suggests that this semicircular annulus between the two the two circumnuclear rings is the site of some intense star formation. There's evidence of an age gradient not only from the center outwards, but also in the northern area of this, suggesting that the rings themselves are the site of intense star formation. And that's data that will be, or that's a paper that will be coming out soon. So look forward to that. And feel free to ask me any questions when you see me around. Thank you.
Helps to get the right one, doesn't it?
All right, next one, Jeremy Drake.
Oh, can we go back a page? Oh, sorry, hasn't played yet. There we go. Hello, everyone. My name is Jeremy Drake. I work in the high energy division here in SAO. Is there anyone else from high energy here? No. Okay, so I work mostly on the. Oh, so you were, yeah. Mostly on the high energy aspects of non-degenerate stellar physics. And for the purposes of this particular meeting, the project, a large project on the Cygnus OB2 association, essentially centered on a megasecond of Chandra data. And of course, as all megasecond proposals for Chandra, they promise to essentially solve all existing problems in any given field. So this one solves all outstanding problems in star formation, especially for massive stars. So why SIG OB2? Well, it's the nearest example of a truly massive star-forming region. Panchromatic survey, essentially radio to X-rays. X-rays find all the stars for you. Infrared gets you all the disks and everything else. We find it's 400 million years old. 30,000 solar masses. We find it's unbound and unmixed. So Cygnus OB2 appears then to be inconsistent with the idea that very massive stars have to form in very dense dense clusters, because Cygnus OB2 is not a dense cluster. Dynamically, we know that it was always an association. It was never a dense cluster, and we can also, in addition to looking at the way the massive stars have been working, we can also look at protoplanetary disks. So the radiation field of Cygnus OB2 approaches a maximum of about 30,000 times the local interstellar value. So a very vigorous environment. And there it is. Here is the survey area outlined in black. You see the MIPS and the IRAC bands in red and green. And the X-ray diffuse emission is the blue. And so the diffuse gas, the hot diffuse gas, essentially fills this sort of this cavity that you see outlined by the Spitzer dust emission. The OB stars are all, if you can see them there, like the white circles. They sort of lie in a bit of a filament sort of shape across the middle there. So my poster is actually on something completely different. I'm sorry, I totally misread I actually didn't read the instructions at all, but the poster is on something else. But I'm happy to talk about this. Thanks.
All right, okay, thank you. So next, Thomas.
So I'm continuing to be interested in star formation in large fragments, and we actually did 2 studies in the last year. We took numerical simulations and asked the question, is Oesterreicher criterion the right criterion to predict fragmentation? And what we actually found is that the fragmentation occurs much earlier in these fragments than predicted by the classical Oesterreicher criterion. What we also learned is, because we now used our observational tools to analyze numerical data, that you have to be very careful with projection effects in 2-dimensional data. So if you're interested in this part, you can go to the paper, which is an RCPH, is actually part of the PhD thesis project of Roxana Gira. The second study is related to the star formation activity in these giant molecular filaments. We now know these filaments, and the question was, are they actually special compared to local clouds, or can we predict the star formation rate if we analyze these objects? And what we actually did, we now combined for these 50 objects near-infrared, mid-infrared, and Herschel data. This was really a huge enterprise, and Mia Shang, our postdoc, did this work. This is really amazing data set. And what we found, and I think that's interesting for Charlie, that is now the star formation rate versus the mass, and that was actually the only correlation we found. These are the local clouds here, and these are the filaments, the giant molecular filaments. So I would claim there's nothing special. They extend the relation to higher masses, but you can still use your mass and dense gas to predict the star formation rates. That's it.
Thank you, Howard. All right, so I have to introduce myself. This is the last introductory talk today. All right, thank you. So my name is Qizhou Zhang. The question that we're worried or concerned is how do you actually take those molecular gas and form the filaments, and then you fragment, form those clumps, and then you form this a young cluster, as you see in this Orion Nebula cluster. As you see that this is question is relevant because we know that most stars are forming clusters, as Charlie Lotte and other collaborators have found. Of course, this is a quite complex process. You have a lot of parameter space to explore, to inference this. And I just want to show you, highlight some of the stuff that we've been doing. And this is a sort of in the realm of filamentary structures. This is work done by Nan Yu, who was a pre-doc here, just left and went back to Beijing. This is an Alman observation of OMC 2 and 3 of N2H plus 1 to 0 transition. What's interesting here is that we found this subthermal
line width, actually subsonic line width here. That this is 1 when the line width equals to the sound speed. And when you look at the lower resolution, you get larger line widths. So this is really actually a challenge idea that the massive stars really form in those supersonic turbulent environment. We've spent a lot of time actually trying to measure polarization to infer magnetic fields, and this is one of the work we've done with the SMA of a large sample, about 20 objects, and in this paper that we published 14 of them. And what we found is actually in the scale of core scale that the magnetic fields tend to be important in doing this fragmentation process. And we're very happy that this entire sample has been accepted for high resolution observation with ARMA in polarization in cycle 5. I just want to highlight this is what's SMA shown here, and this is what ARMA is showing the high resolution. So you see a lot of larger dispersion. And I won't have time to actually talk about other projects. Hopefully you'll show some of them already shown some of those, and you'll share some of those later on here. Okay, thank you. So we're on time, actually. Good. Phil, I think you have the final research talk.
Everybody leave.
I think this is a different.
So it's a different connector.
Do we?
I have
yeah.
Yes. Okay. Do you have a pointer? Laser pointer?
All right. So Phil going to tell us how do dense cores grow.
Hi, everybody. I'm Phil Myers, and I've been interested in dense cores for a while. And let's see if I can make this. Can I advance this? Okay, thank you. I need to go to my bottom. Gotta find it first. Bottom right. Here we go. That one.
It's this one.
Thank you. Yes. Okay. So, what about these dense cores? They are useful because they help us understand star formation. They harbor protostars. They have nearly thermal line widths, at least in nearby clouds. And they can be fit by simple equilibrium models like the Bonner-Ebert sphere. And that's all been very good, and many careers have been built or advanced by doing just that. But equilibrium models do not match some core properties, and as we learn more and more about cores, we see that cores often appear in filamentary chains, not isolated, but have neighbors in their filamentary environment. And that's true in nearby dark clouds, and it's also true in infrared dark clouds, as Chizo's work has shown. Also, some cores seem to have evidence for inward motions surrounding them, as is in these spectra of L1544, extending beyond the core itself, suggesting that there is inward motions onto the cores. And most interestingly, in a single filament or a region with similar filaments, you have a very broad range of masses, core masses, extending a factor of 20 or more. This is in L1495, and this is in the Pipe Nebula, work by João Alves and Charlie. And so this raises some questions. You wouldn't expect to have such a wide range of masses if you had cores in equilibrium with a single surrounding medium. then you would expect to have, if they were like Bonner Ebert spheres, they would all have masses close to the gene's mass. So why such a big spread? That gives motivation for this talk. How do core mass functions arise, or how do cores grow in filaments? So there is a huge literature on the core mass function and models, how to explain it. You can roughly say that there are the top-down models and the bottom-up models. The top-down models are basically turbulent, multi-scale gravitational fragmentation of a big, complex, turbulent system. And we've known for a long time that supersonic turbulence is a great way to make filamentary structures and also cores within them, and that they have a substantial spread in mass. And this has been supplemented in recent years by some nice analytical theories of the core mass function, which do resemble the observations in many regions based on this multi-scale gravitational fragmentation. At the other extreme, you have the bottom-up kind of model, where you have point masses that are pulling mass in from a surrounding medium, so-called Bondi accretion. If you have a distribution, initial distribution of point masses in a uniform medium, then you can start out with a narrow distribution like this, and because the Bondi accretion the rate goes as the square of the accreted mass, the rich get richer, so that means that while the left side of this distribution grows only slightly, the right side of this distribution grows a lot, and it turns into this more asymmetric distribution that you have right here. This is from Hans Zinneker's thesis many years ago, and this has been also pursued in simulations. You start out with a turbulent simulation, and you find that indeed it looks somewhat like the IMF, but it has been interpreted by one school as verifying the idea of competitive accretion, whereas simulations, turbulent simulations, which are somewhat similar in their starting points, have been interpreted as reflecting this multi-scale gravitational fragmentation. What I want to do is do a very, very simple treatment of what you might call competitive accretion in a filamentary chain where the masses are growing by Bondi accretion. So here is the setup. Here are cores with neighbors in a filamentary arrangement. This is the Bondi radius, which gives roughly the sphere of influence, gravitational influence that a point mass has. This kind of treatment is extremely simple. Hopefully it is not too simple, just simple enough. The caveats are that for Bondi accretion models, they are isothermal, non-turbulent, non-magnetic, and you do not take into account the self-gravity of the medium. So that's a lot of simplification. On top of that, in this model, the core is a point mass. It has no structure. So that's another simplification, and we're talking about not an infinite medium as in the original Bondi picture, but one that has a finite extent. What is new and different about this? There's basically just one wrinkle, and that is that each core is expected to start from a very low mass starting point, which means that its sphere of influence is very small. And that's small compared to the spacing between neighbor cores. When you're in that regime, the cores don't know about each other, and they're free to grow spherically. And so early on, they have classical spherical Bondi accretion. The mass accretion rate goes as the square of the mass. But as they get larger, their sphere of influence gets larger. As far as their masses go up, their Bondi radii go up, and they begin to know about the neighbors, and the neighbors are competing for mass in the sideways direction. And so there comes a point where it becomes, where you get much less accretion in the sideways direction along the long axis because of gravitational competition between neighboring cores. So in that case, the accretion rate changes, and because if you shut off the axial accretion, then what's left is primarily what you might call cylindrical. you're getting flow with like these arrows indicate, but not much flow in the sideways direction. So then the mass accretion rate is more like mass to the first power, and that gives you a difference in the subsequent accretion history of the core. And roughly speaking, the spherical accretion gives you a shape to the CMF which sets its slope, and the cylindrical accretion gives you a shape to the CMF which sets the mode. And I'll show you how that works. So here we are with pure Bondi accretion. Here is the initial distribution, the log normal distribution, centered at some relatively low mass, something on the order of 1/10 of a solar mass. Maybe that's the same as Hope Chen's droplets. They start accreting spherically. You see that the rich get richer. So the high mass side of this distribution goes to here, kicks out to high mass and develops a slope. If you keep on going, that slope asymptotes to -1. That's the essence of the CMF of Bondi accretion. But if you don't go all that way, then you get a steeper slope, as is indicated here. Then, if you then accrete from that point forward by a more cylindrical accretion, the nature of the profile has the same shape. You see the blue curve has exactly the same shape as the red curve, but it's translated to higher mass. That's a consequence of the fact that you are now accreting as m dot going as m to the 1 rather than m to the 2. So that allows you to move your CMF shape to higher mass, and that's what it takes in this case to match observations of the CMF in this particular region, the Aquila region, as published by Vera Koneves in the recent Herschel study. So this might be useful because if you have an analytic expression, as we do for the CMF due to this two-step process, you can then use it to fit other observed CMFs. And that's what we have here. We've taken all the CMFs within 400 parsecs that have been published and have sufficient data. And you can see that although the modes will vary from one to the next because of differing resolution and core definition, the shapes of many of them are pretty similar. They have that asymmetry, a steep rise on the low mass side and a fall off on the high mass side. And typically, that slope on the high mass side is not -1, it's steeper than -1. As you can see very clearly here in the case of the Aquila, this is the -1, which would be fit by pure Bondi, pure spherical Bondi, and this is a slope that's more like -1.5 that was better fit by this two-step process. Okay, so how does that look like in terms of numbers? The typical fit values that you do with this fitting of this expression for the two-step process, typical sigma, the log normal of the initial distribution, the sigma of that is about 0.8, and the typical time it takes from start to finish for this two-step process is about 2 free fall times, or about 0.6 million years. Okay, so what can we say about this experiment? Core masses can match observed CMFs by this process of modified Bondi accretion. You start out with an initial log normal distribution. You then have a short period of spherical Bondi accretion. Then competitive accretion from filamentary neighbors becomes important. And the character of the accretion changes from m dot going like m squared to m dot going like m to the 1. And this cylindrical accretion then gives you a slower accretion rate, which allows you to match better to the observed core mass function. Now, this is good as far as it goes, perhaps, but there are a lot of questions that need to be answered. One is, how do you define a core in this case? Because we're assuming point masses. That's fine if you're far away from the core, but they obviously have structure. What is their relation to the initial mass function? When do they begin to form stars? Or alternatively, how do you keep them from forming stars right away if you're accreting in this manner? why don't we have a role for turbulence? Well, maybe Kijou just told us that we don't have to worry about turbulence anymore. But it's probably very important, at least in delivering the mass to the cores. What about the role of magnetic fields? This is a non-magnetic model. What about cores that are not in filaments? Not all cores are in filaments. Do they behave the same way? And finally, do cores form from filaments, as is often thought to be the case, or do they form at the same time with filaments due to accretion flows that bring the gas together, make both at the same time? Okay, thank you.
Time for questions. Lisa?
Fascinating. Well, I have just one question. If this wasn't just strictly one thing and then the other thing, but it was like a mixture of both things at the same time, would you get a different answer?
I think it depends how you mix them. If you mix them, yeah, it sort of depends on the width of the initial distribution. Because if the initial distribution is narrow enough, then that's not a crazy approximation to say first you're mostly this way and then you're mostly that way. But if it's broad enough, then you have more of a transition. So that remains to be answered.
Yeah, I'm just trying to understand what you mean by spherical Bondi accretion. Usually the Bondi accretion is an object moving through some kind of flow. So are you talking about just stuff falling in?
Yeah,
is that some initial condition?
I'm talking about what you were referring to is sometimes called Bondi-Hoyle accretion. That's a moving accretor. But what I'm talking about is Bondi accretion, stationary Bondi accretion, in which case the accretor is sitting still and it's accreting spherically.
Right, but what's
that's the Bondi
that?
1952 classical.
Right, but what's causing the accretion then in that case?
It's gravity. It's still gravity.
So
it's actually more efficient at accreting than when you have a moving.
No, sure, it should be, but how does that then compare to like the standard shoe isothermal sphere collapse or Larson, Princeton? Is this just a convenience to make such a calculation, or is there some?
Well, it's a different starting point because in the shoe case you have pre-assembled all the matter into an extremely centrally condensed structure, self-gravitating structure. But in this case, you're taking a point mass and putting it in a uniform structure. So this is perhaps a better way to describe things that are the early history, because you don't have to posit such an unrealistic assemblage of material to a very, very centrally condensed state. You can start instead with something that's more isolated, more simple in terms of its radial structure. You just plop it into a nearly uniform medium, and it will start accreting.
Does your model assume anything about the boundedness of the cores? A lot of the observational talks have been showing that cores seem to be unbound. Does your model make any assumptions about that?
Well, it assumes that you have a point mass, and that the point mass is able to accrete surrounding gas. So the system of gas, point mass plus surrounding gas, that's gravitationally contracting. So you could say that in that sense it's bound. But if you took the point mass out of the picture and asked, is the medium bound, then it is not.
This is probably a stupid question, but I just wondered if you could perhaps see something in terms of the kinematics, the different accretion modes. So you say, an early evolutionary phase is kind of predominantly in the axial direction along the filamentary structure, and then at a later evolutionary stage, it's kind of perpendicular to that. Just wondering, do you think you might be able to predict something in that respect? You might be able to observe.
Well, predict, yes. Observe, I don't know. Yeah, no, I think that's a very good point. I mean, there ought to be observational signature, and particularly in filamentary chains, which shows, the magnitude of perhaps of the sideways gradient might not be as great as the magnitude of the radial gradient.
Yeah.
Yeah, Phil, going back to your original part of your discussion when you talked about the CMFs and the top-down and bottom-up scenarios. Can either of those scenarios actually, I mean, all of them can get the shape right, but usually to get, like, at least in the top-down ones, to get the actual characteristic mass correctly, you have to fine-tune the models. But then once you do that, you know, that fine-tuning usually doesn't match with the wide variety of physical conditions we actually see where the CMF seems to be invariant to those. So do you have any comment on that?
Well, that's a very good point. I should have mentioned that it's, a lot of people get the shape right and a lot of people get the slope right, the high mass slope right. We're getting the mode in terms of, you know, physical currents, fundamental physics. And there doesn't seem to be much consensus on that. And in the model that I'm talking about, the mode turns out to be a fraction of the gene mass. But there's some variation depending upon how long it evolves. And the gene mass itself, of course, depends on the properties of the medium. So for a higher temperature or a lower mean density, the gene mass is going to be greater, and conversely.
Right. I mean, I thought about this in the past where you could say use a Bonner-Ebert criteria. But the thing is, because that requires certain fine-tuning of, you know, temperature and density, it's hard to match the wide range of conditions that actually are observed, yet the IMF and the CMF seem to be kind of invariant to that.
Yeah, well, that's a good point, and yeah, more work needs to be done on that.
All right, let's thank Phil again. So this concludes the oral presentation in the afternoon. Let's thank all the speakers. To Alyssa for the final session of this afternoon.
Absolutely. So we're just going to put 7 chairs here. Feel free to help me. And then if you were the chair of one of the unconferences, please come take a chair. There we go.
All right.
So if anybody wants to show anything, you can. Here. Do we have everybody? But we should only have 7 people unless we have co-chairs.
Yeah, we had co-chairs.
Co-chairs? Yeah, go ahead. So go ahead, just add more chairs, actual chairs. Where's the one?
If people want to show stuff,
I can show the picture. Right. So do we have? But I don't have. I'll use my computer. Okay, I'll get a computer. So the idea is we don't really need these because now you're sitting and you know what your conference was about. So we can start from one end to the other and then summarize. I volunteer Thomas.
So you had a very interesting,
Mark, we have till 6 o'clock, so
okay.
It's about 5 minutes per unconference total, so use it however you like.
So we talked about polarization. It was a very lively discussion because we are all really amazed by the new ALMA data. I mean, we have seen one set on the slide. So one discussion was about the more massive clumps cores. And I think here we really see that the magnetic fields are responsible for the polarization. But then we also talked about the embedded disks, and in this case we have a second mechanism which was a bit unexpected, which is scattering by large particles. And in the case of HL tau, you now see that both mechanisms are at work, so that you actually need multi-wavelengths data to see one or the other mechanism. And then we have seen Sarah's data. I mean, you showed it again. You're still puzzled that you see the spiral structure. I think in the cores, again, we see evidence for scattering because the cores are really optically thick. And scattering is a better mechanism, which would mean that even in this early phase, you would grow particles to very large sizes because you need the size compared to the wavelengths. You measure the scattering properties. So that was more or less what we discussed, and I think Sarah, do you want to add something? Or? And you should really see the beautiful HL paper where this is nicely summarized.
Yeah, I've recently put a HL thing on archives kind of showing multiple polarization mechanisms at 3 millimeters. Seems like grains are not aligned with magnetic fields. It's not scattering, but it's aligned with radiation anisotropy. It's set at 870 microns. The polarization, and this is all a disk. The polarization that's like scattering at 1.3 millimeter. It's mixed between grains aligned with radiation anisotropy. So that means that grains are aligned perpendicular to magnetic field, or sorry, no magnetic fields, perpendicular to the radiation field. And scattering at band at 1.3 millimeter. It's a mix between these two morphologies. So you have band 6 data of disk. It's almost a 1.3 millimeter stuff polarization. It's not something easy to interpret, especially with one band. It's tough and really need multi-wavelength, especially because you already see at 1.3 millimeter you got a mixed polarization mechanism that's happening.
Does this depend on scale?
Yes. Just to, when we're talking about everything, the only time you're seeing scattering in this alignment with the radiation anisotropy, so grains aligning perpendicular to the radiation field, we only definitely seem to see this in disk. So if we go to stuff larger than disk, so like an envelope or a core, I think we're still predicting that's all magnetic fields. I think we still want to do some multi-wavelength tests to make sure that's actually true. But even at the envelope scales, we've got some other high-resolution stuff. You're seeing hourglass morphologies and things like that you wouldn't expect from the other mechanisms.
I guess the feeling also was it was kind of disappointing that you can't really use polarization to effectively probe magnetic fields in the disk, but then use that polarization data is quite sensitive actually to the maximum size of the dust.
I think we really got a new tool to determine the maximum size.
Very effective tool.
So we can leave the beta exercise.
And we did discuss alternative ways to try to probe magnetic fields in disks using Raman splitting or polarization of molecular light emission as a tracer rather than polarization of dust, because it appears that will not be the main way that we will be able to probe this, at least reliably. So for those who are interested in constraining magnetic field strengths in disks for MHD simulations, we need to be a bit more creative in how we do that. Going forward is pretty much the outcome of all this.
Sounds enlightening and depressing at the same time.
It's exciting from the dust side, not the magnetic field side. Let's put it that way.
We will.
I think it's pretty exciting because we now have a new tool.
Oh, me? Okay, so we talked about...
Sorry, actually, we're here for a separate conference.
Yeah.
So we were co-chairing along with Elaine Winston, who had to, unfortunately, leave the GWST brainstorm, what is it all about, and what can we do with it on a conference session. And we didn't really write down much in the way of notes, so this is going to be very, very brief. But we went over what projects people had been part of and what kind of capabilities, what instruments are on the telescope, what projects were inevitably accepted for the early, I guess the cycle 0 equivalent, early science, and what also overheads to expect. You were looking up the slew times for the telescope, how long it takes to go from, between two sources that are 20 arc minutes apart versus a set of degrees apart in order to, figure out whether or not a large survey of multiple sources is doable.
It moves very slowly.
Yes, which was the conclusion. So we then also talked about whether or not you can do observations with instruments in parallel, or if you had to do one instrument at a time. And then, what sort of projects people in the room had already been thinking about or considering, from looking at clusters to looking at disks, using, chronograph to using spectroscopy. It was, it was just a very calm and very relaxed conversation because there was no pressing deadlines anymore. And then also when the next call is going to be, and when the instrument is actually going to be launched, and when science is actually going to be officially taken. So it was.
Yeah, and I think real quick, there's only one thing that was really star formation, so that means it's a lot that you can do.
Possibly
so,
2 projects out of 10 that have tangential star formation relations.
Can you tell us what those 2 are?
So one was looking at feedback from high mass stars, and then the other was looking at ICEs, I believe in low mass environments. So those were the 2 projects that got time. I don't remember what hours for each. Everything else was extragalactic. So if you want to, I think, do extragalactic star formation, JWST is definitely moving in that direction.
Or exoplanets.
Or exoplanets. That's true. There were a number of exoplanets.
Has anybody talked about using the same instrument in parallel, like with different processing pipelines? Because I think, like, if you're looking at radio arrays, you might partition, a set of antennas to do certain kinds of beamforming, certain observations, while the other part is doing something else.
I don't know. I imagine it has to do with how the light path to the instrument works. Not everyone in the room was even aware you could do the instruments in tandem, so we did not discuss whether or not you could split up a single detector to do different modes within one detector. I do not know the answer to that. Open floor.
I don't think the instruments support different modes. I mean, the number of instruments that you can use to do simultaneous observations are pretty limited, I think, by data volume in general.
Oh, and then one other thing we discussed was how JWST fits in with future and current near-infrared instruments. And moving forward, if you want to use JWST, you need to come up with a project that really emphasizes why you need a space-based facility and why you can't do this project from the ground. So I think that was something that Ilsa was stressing as well.
Somebody brought up GMT.
Yeah, I think Ian was the one who brought up GMT.
It was just mostly like what we were talking about, what the overlapping science was. There's some overlaps, or much longer
Anyway, that was our very brief overview of JWST ideas.
Okay. Yeah, so our session this morning, I'll show a picture, kind of outlines what we discussed. So our session was about multi-scale, like star formation simulations. So all the way from that's okay. So okay. Okay. So basically, the idea is, you can read it. We went from, like, when you're talking about star formation on, multi-scale, you're talking from all the way from stars where they actually form, but also going all the way up from stars to disks, and then star clusters and so on, filaments, whatnot, all the way up to the universe itself. And so one of the biggest challenges and trying to model like star formation on all these different scales, so doing galaxy simulations, cosmological simulations, and so on, is trying to figure out like what physics is actually possible to include, and what do you need and what can you get away with. And so the nice thing was we had a mix of observers, star formation simulators, ISM simulators, large scale like cosmological people, and so it was really nice to have this big discussion about what are the costs people cut in the type of simulations. So we discussed a lot about like illustrious compared to fire simulations. Also talking about small scale simulations, about how like if you actually want to study how stars form, you need to pay more attention to the physics. You shouldn't be putting the subgrid physics in because you really need to understand how feedback will actually interact with the ISM. Whereas in cosmological simulations or galaxy scale simulations, you're using, you know, it's like for illustrious, you're using the observations to kind of mode the subgrid physics that you put in to try to get the correct relationships at the end of the day when you're matching the results from the illustrious galaxies to galaxies that have been observed. And then that kind of led us to start this. Oops, sorry, now zoom down. Oh yeah, and then we talked about all the physics. So like we went through all the phases, and we were just like, okay, what are the different phases of gas? And we talked about like dense cold gas. We talked about, you know, ionized gas, the WIM, the HIM, all those, the warm neutral medium. And the fact is, like, if you want to actually get, like, basically it's a really hard problem to simulate all these in one coherent picture. And so, like I said, like, you know, as simulators, you have to cut corners. And then, so this led Alyssa to be like, we need to create a spreadsheet to kind of just summarize about what has been done. And so, and this should be open to everyone. And the cool thing is more just kind of like, let's see, got it. Where we're trying to kind of just compile all the stuff, like all the papers, to get an idea of what are the scales that have been done for star formation simulations, what are the physics that have been included, also get an idea of the different codes that are used. So for example, there's many different ways that you can simulate these things. So right now, like with the repo, you have and Gizmo, codes like that, you have this moving mesh system, whereas for Flash and Enzo and Orion, you have adaptive mesh refinement. Furthermore, you have SPH for the big, like, cosmological simulations where you need to basically just follow dark matter. And then, so we're just trying to compile this list of all the stuff so we can get an inventory of what's been done and what needs to be done and what are the limitations of the work. And as you can see, it's like, oh yeah, so you can see most of this stuff that is actually with links is mine. Blake's work is we added that stuff, so feel free to add stuff.
Well, I added a lot of names. So
yeah, I saw that.
This is where this chart, everyone should add their favorite interesting work, and then I'm going to at least add one work from a lot of people that I think are doing cool work. So that's why there's a lot of names there, but not a lot of data. So feel free to
yeah. Oh yeah. So like for example, we're okay, sorry. Yeah, so like I said, you know, we want to kind of have inventory of the papers that's been done, and then also kind of take into account what physics and stuff has been included. So for example, do these simulations have gravity? Do they have magnetic fields? And probably most of the time the answer would be no. Radiation, so on, chemistry, and so to kind of see like kind of what the state of the field is right now, what people are focusing on, what like the direction that we need to go. Also, what types of simulations do these different codes produce? And also the fact, you know, we talked about for some of the codes, it really depends on the development that's been done. So Orion, for example, has been mostly focused on star formation, and so the physics included, the opacities, etc., and the radiative transfer and stuff included was kind of in that context where now you have these other codes like Flash and Enzo, which are public, and so people are adding whatever codes they can. Because the thing is, all of these codes should be able to apply. Should do any hydrodynamic problem, whether it be galaxies or stars, but what you want to model and kind of the physics that have been done. So, yeah.
And then Blakely also has this other site, CATS, which is wonderful, that shares the examples of catalog of simulations. So we'll send those links to everybody, but we need to.
Oh yeah, sorry.
So, sorry.
Right, so we had a session on data science /AI/discovery, what can all these techniques do for you? And so far we've focused on better understanding where the needs are and what people are using today and where we should go as next steps. And there was a very lively discussion about sparse data and training sets that have to be created in the simulations. That was in the context of Planck data. And Juan Soler is going to present more details on this on Wednesday, I believe. Then we had another piece of discussions where we were focusing on spectral line observations, how to decompose molecular line spectra, how to identify structure, what are the observables, and what are the things that we actually want the algorithms to fish out of this data. And that was an area where people looked into statistics and hierarchical clustering, and among others. Then we had a piece on galactic ring survey and interferometric data. Here, Gaussian mixture models were mentioned as one technique to decompose things into something that you can look at more systematically. And then towards the end, we were also discussing the applicability of neural networks. Dr. Fickbarner said that he sees neural networks as continuous function approximators that are very promising. Concerning the discussion that neural networks can't really explain what they're doing, we kind of converged to a way of looking at this where you can use neural networks for hypothesis generation. So the neural network comes back and says, oh, I think these pieces are interesting, but then you need something else to generate the final answer and produce more scientific rigor and the explanation that you would expect in the scientific community. But then, to summarize, we kind of asked ourselves, where should we go next? Like, how can we engage in the community to make like the next steps? Because on the one hand, we have the data scientists, the computer scientists who kind of drift off in doing more and more complex things, but kind of don't have the connection to the applications in astronomy. And then on the other hand, astronomy is getting more and more data, but both people need to interact, because the highly skilled computer scientists won't necessarily go off and learn astrophysics, whereas the core astrophysicists won't necessarily go off and improve things in computer science to advance computer science. So we need something in between. We need bridge people and like interdisciplinary courses. So we need interactions with data science. So one thing could be through education. Like think of courses where we educate the next generation of students or PhD students with people actually lecturing from both areas. And another way could be to co-locate at major conferences, have like a workshop. So for example, we can think about having a workshop associated with the AAS in one year and then go to a major ACM computer science conference the other year and then go back and forth. Because that could be the way to engage people who are at these big conferences anyway and would like to take a peek into what's going on in these fields. Computer scientists are highly interested to learn about real problems. Like most AI people I meet these days are really looking into, what can I do with applications of neural networks or the things that work on to show impact as it works on many fields. So that's going to be
I just heard that the visualization conference, IEEE is going to have an astronomy and visualization.
Yeah, I think that's the right path to engage. And then on the other hand, we can have computer scientists come to astronomy conferences. So we immerse into these fields. So these are just two concrete suggestions, but there's way more to be done. This goes probably beyond this meeting, but again, this is food for thought.
I shared the session about simulations, double arrow observables, which was supposed to be meant to be the interaction between simulations and observables. And it was a fairly relaxed conversation. It gravitated very strongly toward complications of lines of sight confusion that we're stuck dealing with in both observations nearby and observations far away. So we talked a bit about different types of observations and then different ways in which they're confused along the line of sight, different ways in which whatever physics you're trying to understand is complicated by the fact that we don't see a clean picture. And then the conversation kind of migrated toward what type of observations we might want to talk about. I mentioned, some works that she was doing with dust observations. You'll see some work tomorrow about line predictions, and that was so basically, the typical ISM observables that you see. But one of the real interesting so we ended up with three things that we kind of might want, like from the conversation,
And one of them was a pretty strange, or a little bit of a strange thing, very specific, which was the possibility of having a safe, reduced chemical network that people could actually use in their simulations. And the idea would be, you know, it might be worth looking into whether or not we can come up with a chemical network that can produce, you know, abundances and, you know, excitation conditions for certain species that if we were to include a full chemical network would be just too costly. But can you come up with a safe, reduced chemical network that would actually let you get meaningful science out for individual species that we're not doing right now? And, you know, maybe that's worth looking into. What species could we do that we're not bothering to predict if we just limit ourselves instead of trying to bite off more than we can chew? Another question kind of came to, you know, asking about, you know, it's really unfortunate when an observer tries to convert their observation into a physical parameter, because they don't observe physical parameters, they observe observations. So it might be useful, but again, the journals aren't set up this way. Journals want you to do science. They want you to make an interpretation, and you know, I think it would be a good idea to waste a little extra space and maybe, you know, publish a little bit more raw data, a little bit more explanation on raw data, so that when simulations start doing observations, they have something more directly and more easily compared, that they can easily compare to. We also talked about, you know, what tools might an observer want, and they might want, you know, one of the things that came up a number of times was means possibly for understanding kinematics, and maybe using kinematics and something else to diagnose structure along the line of sight.
Okay, so we had a small group, Hector and Hope, myself. The session was how do you improve on virial analysis. We started just by asking Hope some more questions about his droplets, which is very interesting. You know, Hector showed some really nice data from the Harvard-Heidelberg project, so maybe there could be some analogous structures there. You know, one question, you know, we brought up some questions and have too many solutions with our small group, but I don't know, we just tossed around the idea of, you know, if we have this external confining pressure that people speak of, but we weren't sure if it's been shown through simulations or whatever that you can expect the turbulence outside of your quote-unquote core to actually provide this kind of isotropic confining pressure, or, you know, will it not be balanced? So that I think is a worthwhile thing to look into. Also, the point was brought up for the virial analysis. I know when I was writing a paper with Jens Kaufman, we pushed back in my initial virial analysis. He's like, Shay, if you're comparing alpha to 2, pressure confinement is already included in that. So if you're trying to include it, then you're going to be double including it. So overall, I think we all need to be careful talking about virial analysis. What critical parameter are we actually comparing to? You know, if you are comparing to 2, you know, go back and look at the literature and see if they're already folding in things like density gradients within the core and external pressure. You know, what could we do going forward? And oftentimes we're comparing really high resolution spectral line data to Herschel, you know, column densities that are involved to 500 microns. Some talks have been presented to do better than the 500 micron resolution. You know, perhaps we could go to, you know, really high signal to noise spectral line observations in regions where the abundances are sort of well understood. You know, maybe we could get you know, the gas column densities from that compared directly to the line width that we're getting from those species. So yeah, those are some of the ideas discussed, and you know, we talk in the larger group from somebody who couldn't make it, and we get pushed harder on this to see what virial parameters actually mean to us.
And, by the way, part 2 of unconferences is totally about.
Right, the last in the circle here. So we had an unconference about our Thor survey. So for those who don't know Thor, it's the H1OH and recombination line survey of the Milky Way, which we're doing with the VLA. So it's the atomic gas, the molecular, and the ionized gas. So we survey this from a large fraction of the inner Milky Way. So I started with giving a little bit of an overview of the survey, where we are, what kind of data products we have from the atomic, the molecular, and the ionized gas. And then we dived into very different topics. So for one, we started with our continuum, where we identified 76 new supernova remnant candidates. And then we spoke Victor suggested what he said already before in his session, that if one thinks of machine learning, that it's sparse sampling with 76, but that one could think of model interpolation of this sparse sampling to get kind of a dense sampling, that one may try to do machine learning with this approach, which I wasn't so aware of these modeling and dense sampling. So that was one thing we talked about. Then we looked at our H1 data, the HISAs, the H1 self-absorption data, and different approaches. Alyssa pulled out glue, and we did a direct comparison of the H1 and the CO data from the GRS survey in glue, tried to see what one can get out of this part. Very different things. Then Juan presented his HOG, histogram of oriented gradients analysis, how one could try to connect the H1 and the CO really on a statistical way, and Juan does the same game to see what these observational signatures, what are there in simulation. So he takes simulation from Patrick Hennebel with and without supernova remnant feedback to see how the signatures in these HOG analysis vary and what one can extract from the data. Catherine showed some of her results of the giant molecular filaments, which wiggle around the spiral arm velocity, which I still don't understand yet, but that's something we have to think more about. What else? Did I forget something? But that was a very diverse discussion about the different applications we can do within Thor, and lots to be done.
Okay, great. So that's wonderful. And somewhere here, there's a few pieces of paper. I'll put them up in a minute, but the plan now. So first of all, let's thank all the people. And so you're dismissed, other than to have dinner. So some of the local people, like me and the other members of the LOC, will take you to restaurants of your choice. So just mill around and see what we're proposing and see where you'd like to go. But it's only tomorrow night where there's a formal dinner, and so whatever you like. You like? Personally, I'm thinking Chinese food. So. Okay. Anyway, so thank you. And tomorrow morning, what time?